So in today's lecture, we are going to see the relation between the autocorrelation function and the power spectral density. So they both form a Fourier transform pair, which is also known as a Wiener-Kinchy relation. So autocorrelation is nothing but it tells us a similarity between the signal and the shifted version of the signal, and the power spectral density tells us about the power contained in the signal at different frequencies. So let us go into the proof. So we are defining xt of t is nothing but x of t when t lies between minus t to t and 0 otherwise. So from the general Fourier transform formula, we know that x of s or x of j omega. So we are applying the Fourier transform for xt. So xt of j omega is nothing but the general formula which we already know. And from the Parseval theorem, we also know this relation. So in order to find the average power, we need to divide this equation with 2t. We need to tend t to infinity and also take the expectation of this. So we need to apply the said conditions on both sides, that is divide with 2t tending t to infinity and applying the expectation of x of t. So this is nothing but the average power, and so we need to apply the same thing even on RHS side. So I have done the same thing. So we are applying limit t tending to infinity, dividing it with 2t and applying the expectation. So now this is nothing but sxx of omega. So now we already know what is xt of j omega. We have already defined previously that xt of t is nothing but x of t when t lies between minus t to t, and that formula of the Fourier transform is this. So the same thing we are applying here. Now we are having whole square, so we are writing expectation of xt of j omega whole square can be written as expectation of x of j omega into x conjugate of j omega. So x conjugate, so we are opening that, so we get nothing but integral. So one we are writing it as j omega t1, the other one we are writing it as minus j omega t2. So one, since we are having whole square, one will be t1 and the other one will be t2, right? Now afterwards, what we are doing is we are just rearranging the terms. So rearranging means what? We are taking the expectation inside and we are writing it as expectation of x of t1, x of t2, and here we are taking the minus j omega common. We get the same thing when we open the bracket. So now I have already told what is the formula of the autocorrelation. Rxx of t1 comma t2 is nothing but expectation of x of t1 into x of t2. So we are replacing this thing with Rxx of t1 comma t2. So we got this. Now after this, what we are doing is we are just applying the inverse Fourier transform of sxx of omega. That is nothing but we are just taking the Fourier inverse of sxx of omega. That is nothing but the power spectral density. But what is sxx of omega? We already know what is sxx of omega. That is nothing but this equation, right? So now the Fourier inverse formula also is nothing but 1 by 2 pi minus infinity to infinity sxx of omega e power j omega tau t omega, because we are applying the Fourier inverse. Okay. By substituting the xx of omega value, we got this equation. Now what we are doing, we are just rearranging the terms by taking 1 by 2t outside, limit t tending to infinity outside, and we are keeping this all together here like 1 by 2 pi integral minus infinity to infinity, and from these two terms we are taking j omega common, then we get this equation. Okay. So now we already know what is the Fourier transform of impulse function. That is, Fourier transform of impulse function is nothing but 1. And if we take the inverse of that, we get del of t is nothing but 1 by 2 pi. This is nothing but the inverse Fourier transform formula. That is 1 by 2 pi integral minus infinity to infinity 1 into e power j omega t d omega. So now we have seen from this what is this value. It is equal to del of t. But the similar thing we are having here, but instead of t, we are having tau minus t2 plus t1. So this fill will be equal to del of tau minus t2 plus t1. That's what I wrote here. So we are substituting this instead of this, and we get this equation. So after getting this equation, from the properties of impulse, limit minus t to t, del of tau minus t2 plus t1 will be equal to 1. When t2 will be equal to tau plus t1. That is from the properties of the impulse function. So this fill value with this integral and dt2 will be equal to 1. So we got this equation. Now what we are doing, we are just taking t1 as t and dt is equal to dt1, and what we get the time, we'll get this equation. That is nothing but we are taking t1 as t, and from here t2 is nothing but tau plus t1, but t1 is nothing but t. So this is nothing but the time average of the autocorrelation function. So I have already said you all previously that the power spectral density and the time average of the autocorrelation function form a Fourier transform pair. So that is what we have proved here. But if the autocorrelation function is a WSS process, that time we can say this will be equal to Rxx of tau. This full time average will be equal to Rxx of tau. That is, Fourier inverse of Sxx of omega will be equal to Rxx of tau. And if we take the Fourier transform, inverse Fourier, that side becomes a Fourier transform, and we get this equation. And simply Sxx of omega is nothing but the Fourier transform of Rxx of tau. That is nothing but minus infinity to infinity Rxx of tau e power minus j omega tau d tau. Or if we want to apply if we want to find the Rxx of tau, we just need to apply the inverse. So this is nothing but the Fourier transform pair. It forms a Fourier transform pair, that is the autocorrelation function and the power spectral density.